Hi everyone, I'm Ivan from Vienna University of Technology, and I'm going to present our paper about increasing traffic safety with real-time edge analytics and 5G, co-authored with Vincenzo De Maio, Klaus Polhammer, Ivan Bodrožić, Josip Lasic, and Ivona Brandić. This paper has been partially funded by the city of Vienna and FWF Start Prize and supported with NetIDEE by Internet Foundation Austria. I would like to start my presentation with a real-world example that motivated our work. It's about ensuring traffic safety, as traffic accidents represent critical global issue causing injuries and deaths. According to the report by European Transport Safety Council, just in EU in the last 10 years, there were more than 50,000 pedestrians and 20,000 cyclists killed on EU roads, accounting almost 30% of all EU recorded deaths. Also, in many EU old cities were historically growing, they initially didn't plan for a modern traffic infrastructure. And here we have a typical example where we can illustrate the critical situations of poor visibility when pedestrians, animals, cyclists can appear outside of drivers' field of vision. For example, behind a roadside bus station or behind bushes. On the other side, we have driver's brake reaction time measured around 1.5 seconds on average, apparently not enough to avoid many accidents. Our goal is to support decision-making by providing early warnings to drivers about these critical situations based on real-time edge analytics. However, edge analytics as a challenge is not specific only for traffic safety, but it's a general problem that we can find also in other similar edge deployed applications such as e-health, such as like smart buildings, smart grids, and so on. In this generic context of geographically distributed machine learning, data that are coming from edge deployed cameras and sensors can be analyzed for near real-time analytics and decision making, and then these data or results of analytics can be further anonymized and used in the cloud for non-critical and long-term strategic analytics. For example, optimizations for actions in case of accidents for police and ambulance. Then we can have strategic planning of low emission zones for polluting vehicles in smart cities, then intelligent traffic management during congestions, and so on. In distributed machine learning, dispersed data collections represent issues in deploying and maintaining accurate global models. But in this paper, we focus on edge smart traffic scenario, particularly near real-time inference and timely traffic warnings. We also aim to investigate design choices and practical implementation of this to solve this problem and making this solution as a generic that can be also extended and used in different other applications. On this slide, you can see a figure that shows an overview of the proposed architecture. We consider exploiting potentials of edge computing and emerging communication technologies. In first step, pedestrians, cyclists, animals, children can be captured by edge deployed camera on smart traffic light, and these video frames are constantly streamed to edge processing module that will run object detection modules. Edge processing device are also integrated on smart traffic light, and results of edge processing are detected objects that are then forwarded as notifications to drivers that are approaching critical intersection. We consider different critical requirements. First and most important is to have low latency. In our setup, latency is made out of both computation latency and communication latency. And then we have privacy preservation, meaning that we should not send any sensitive information or store them through the network. And we have physically space limitations where we need to deal with edge resource constrained devices that we plan to place in such small spaces on smart traffic lights. Regarding computation component is responsible for real-time processing of data that are coming from edge sensing devices. In this figure, we show the average inference time per single frame on different edge node configurations. We first collected different frames from target intersection because we selected a critical intersection in the city of Vienna, and then we use these frames and check different object detection models on them. Considering our physical space limitations, we employed different Raspberry Pi devices like Raspberry Pi 3, Raspberry Pi 4, and their combination with Edge TPU or USB accelerator that acts as a coprocessor to further increase computational speed and reduce overall latency. Regarding software part, we consider pre-trained neural network-based object detection models that can run on these such lightweight devices, and we have these MobileNet SSD version 1 and version 2. As we can see, Raspberry Pi 4 and Edge TPU gave overall the lowest latency. Although version 1 has slightly better results, we further check the confidence scores, meaning a cutoff threshold for accepting detection results. And MobileNet SSD version 2 for our dataset showed a better inference score of 16% of average. Here you can see a traffic light chamber that is provided by our partner Svarko Futurit, and we integrated Raspberry Pi 4 together with white USB accelerator and 8 megapixel camera module version 2 integrated on top of Raspberry Pi. Regarding communication part, we consider different requirements such as a minimal message overhead to keep the transfer time and latency low, and we need to also guarantee the delivery of messages on end users. Based on our comparative study of different protocols that are used in real-time latency applications, such as IMQP, CoAP, DDS, and MQTT, we focused first on publish-subscribe-based protocols, meaning that in our setup, edge devices and edge cameras can act as a publishers, and we can have end devices or drivers phones that can be subscribers to different topics of representing critical intersections and receive these messages. MQTT, message queuing telemetry transport protocol, in this case allowed us for these event-based notifications and target such drivers that are approaching critical intersection. Also, it offers centralized processing as more desirable than a distributed protocol like DDS. MQTT offers also different quality of services, and QoS 0, the messages are delivered at most once, meaning there is no guarantee on the message delivery. On QoS 1, messages are delivered at least once, and for QoS 2, exactly once, meaning we can have also multiple replicas of messages. In our case, on self-developed application, we ran this evaluation on different network types on 3G, 4G, and 5G. And for QoS 1, we achieved under 100 milliseconds for 5G, that is within requirements for road safety applications. And at the same time, we guaranteed the delivery of messages. Next, we know that latency is also impacted by the placement of the MQTT broker. For this reason, we placed first our MQTT broker that is forwarding the messages to the subscribers to Tailwind's infrastructure that is deployed in the city, and we had MQTT broker cloud service. Based on QoS1 on this figure, you can see that we can reduce network latency for when comparing edge-placed versus cloud-placed MQTT broker for 4G around 50% and around 47% for 5G. We deployed our solution on real-world intersection. In this smart traffic light, we placed in traffic light chamber above Raspberry Pi 4 with edge TPU and integrated camera. And then on this traffic chamber below the traffic light, we placed 5G hub that is then connected to 5G network. 5G is set exclusively for this prototype deployment. And in our scenario, once pedestrian or cyclist is approaching critical crosswalk, results from different edge nodes and edge cameras are then aggregated, and audio and visual notifications are sent to driver's mobile device. On the driver mobile device, we have developed application that is showing this notification overlay. Location of the phone is based on mobile phone's GPS, meaning that the drivers, once they are approaching the critical intersection, they will start getting these messages and notifications. For 5G, it is around 108 milliseconds, including both a latency of computation part and a latency of the transferring these messages of communication component. To summarize our main contributions, we show the potential of edge computing and communication technologies to detect critical situations on intersections. And here we ran pre-trained neural network-based object detection models on lightweight devices such as Raspberry Pi 4. In our setup, we achieved and guaranteed a low latency, where that is within requirements for road safety applications. And we also preserve privacy in the way that we didn't send any sensitive information like people's faces through the network. We only send the numbers of detected objects or classes that are detected through the network to the end devices. Our solution showed as a promising step towards supporting real-time decision-making, but not only in this smart traffic scenario, but also it can be extended and considered in different other edge deployed applications. However, we have also further challenges. Currently, our application, once it is started, it automatically subscribes to topics of critical intersections. And we aim to investigate now location-based subscriptions. Then, based on the achieved evaluation results, and achieved latency, we would like to investigate the effect of distance and warning timings on driver's brake reaction time. And we would like to investigate resilience of edge processing to different node and network failures, meaning that our application is running without stopping. If you would like to know more details about in our paper, you can access the full paper version, and here is also DOI link provided through QR code. This is the end of my presentation. If you have any comments or questions, feel free to contact me or any of my co-authors. And thank you for watching and listening.